Hello everybody, so in this video we're going to continue with Chapter 14, Integral Calculus 1, and it's the last topic on the chapter, which is 14.8, Modeling Linear Motion. We start with displacement and total distance traveled. So there's a few concepts here that have to be very clear. The first one is velocity. So velocity, notice that it is the derivative of the position function. You can see that right here. S represents position. So velocity is the derivative of the position function, and it is a measure of how fast a particle is moving and its direction of motion relative to a fixed point. So velocity includes direction. For those of you who are in physics, you know that velocity is a vector. So velocity requires of direction, and it is in relation to a fixed point, usually the origin. Speed, which is the next concept here, is the absolute value of velocity. And it is simply a measure of how fast it is moving, and it does not include direction. So speed is the magnitude of velocity. And very importantly, it is always positive. Finally, we have acceleration. And acceleration is the derivative of velocity, and it's a measure of how fast its velocity is changing. Okay, so here we are in example 14.37, and it says the displacement s of a particle on the x-axis relative to the origin is given by the position function s of t is equal to minus t squared plus 6t, where s is in centimeters and t is in seconds. So A, find a function for the particle's velocity in terms of t. Graph the functions s of t and v of t on separate axes. Okay, so basically all we have to do is find the velocity function, which is the derivative in terms of time of the position function, which is minus t squared plus 6t. And this is going to be obviously a linear function, minus 2t plus 6. So now let's take a look at the graphs. Okay, so here are the graphs. Notice that the position function is quadratic, and because the velocity function is a derivative, this one is linear. And there are the graphs on two separate sets of axes. For part B, they want us to find the particle's position at the following times: t equals 0, 1, 3, and 6 seconds. So basically all we have to do is plug these values into the position function. So notice that s of 0 is going to be 0 centimeters. S of 1 is going to give us 5 centimeters. S of 3 will give us 9 centimeters. And S of 6 is going to give us 0 centimeters again. Now, and remember that the graph was an inverted parabola, so it is obvious that it's after 6 seconds, you would get back to position 0. For part C, they want us to find the particle's displacement for the following intervals: between 0 and 1 seconds, between 1 and 3 seconds, between 3 and 6, and finally between 0 and 6. So here they want the displacement. So displacement is not the same as distance. That's something that you have to be very careful with. What is displacement? So displacement is not equal to distance. What does this mean? Okay, let's suppose that you start here from point A. You start walking from point A. This is like a real life example. And you go up a hill, and then you go somewhere else and then turn around and go, You just walk around and walk around, and then finally arrive to a point B. So displacement is actually this distance from A to B. This little distance from A to B, because it's your final position minus your initial position. That's what displacement is. Whereas distance is this whole trajectory, right? It's everything here. It's all these meters or centimeters or whatever it is that you walked. So that is the difference between displacement and distance. Okay, so basically we would say that it's a change in position. So from 0 to 1, including, right, the endpoints, the change in position would simply be subtracting, in this case, s of 1 minus s of 0. And these values we found before. We said that s of 1 was 5 and s of 0 was 0. So that means that from 0 to 1 seconds, the displacement was 5 centimeters. And we do the same for the rest, right? So it's always a change in position. So in this case, s of 3 minus s of 1. And in this case, it's going to be 9 minus 5, which is equal to 4 centimeters. Notice that we just keep doing the same thing, right? Change in position, which is the displacement. So s of 6 minus s of 3, and s of 6 we said was 0, right? 0 minus 9, and this would be negative 9 centimeters. And then finally, between the change of position between 0 and 6, notice this change of position. And this would be s of 6 minus s of 0. And this is going to be 0 minus 0, 0 centimeters. So what that means is that the particle ended up at the same point where it started. And then finally, for D, they want us to find the particle's total distance traveled for the following intervals: between 0 and 1, 1 and 3, 3 and 6, and then the total from 0 to 6. Okay, so when you want to find distance traveled, you have to be careful with one aspect of this. And you have to be careful with the change in the object's motion, a change in the direction of the object's motion. So that occurs when velocity equals 0. So we have to find for what value velocity equals 0. So let's recall that the velocity function we found was minus 2t plus 6, right? So when does this equal 0? We could have also seen it in the graph, but let's do it algebraically. So this is going to be, obviously, t equals 3. So there is a change in the direction of the object's motion at t equals 3. So that's something we have to take into account. Now there's no change of direction between 0 and 1. So all we have to do is the absolute value, right? Because we're not doing displacement, but distance, total distance. So for that, we use absolute value. So absolute value of s of 1 minus s of 0. And that was simply 5 minus 0, which is just 5, right? 5. And don't forget centimeters. Between 1 and 3, it's going to be s, absolute value of s of 3 minus s of 1. And then we got that this is 9 minus 5, which is 4 centimeters. And then between 3 and 6, which is this one here, the next one, we would do s of 6 minus s of 3, absolute value of this. And notice that this is going to be 0 minus 9, and that's going to be 9 centimeters. Okay, how about from 0 to 6? So that's why I said that we have to take into consideration the change in the direction of the motion at time equals 3, because that's when the velocity is equal to 0. So that means that the object or the particle is stopping and changing direction, right? What we have to do then is do these separately. So we would say, okay, what's S of 3 minus S of 0, an absolute value, plus S of 6 minus S of 3, and again, absolute value because we want the total distance. So this is going to equal 9 minus 0, absolute value, plus the absolute value of 0 minus 9. And notice that this is going to give us a total of 18 centimeters. So remember that when we calculated the displacement, we got a displacement of 0 because we said that the object basically moved 9 centimeters and then came back 9 centimeters and ended up at the same point where it started. But if we want to find the total distance, well, that would be, of course, 9 plus 9, which is 18. So a corollary of the previous example is the fact that if you are given the velocity function for a particle moving along a line, then the integration from a to b of the velocity will give you the displacement from time equals a to time equals b. And if you do the integral from a to b of the absolute value of velocity, then that will give you the total distance traveled from time equals a to time equals b. So in example 14.38, they say the function velocity as a function of time is equal to sine of pi times t, which gives the velocity in meters per second of a particle moving along the x-axis. A, determine when the particle is moving to the right, to the left, and stopped. If it stops, determine if it changes direction at that time. Okay, so basically what we need to do is find at which time the velocity is equal to 0, because that's when you would have a change in direction, right? Whether it's going left or right. So a negative velocity means left, a positive velocity means right, and then 0 means it stops. Okay, so that means that we have to solve the equation sine of pi t is equal to 0. So where is sine equal to 0? Well, remember that sine is equal to 0 at any k times pi, where k belongs to the integers. That's when sine is equal to 0. And you can figure that out with a unit circle, right? Sine of 0 is 0, sine of pi is 0, sine of 2 pi is 0, sine of 3 pi is 0, etc. So that means that we have in this interval that we're talking about, let's see if they talk about the interval here. Yeah, right here. So this is the interval we're going to be working with from 0 to 3. They didn't declare it at the beginning, but that's what we're using. So from 0, including 0 to 3, sine is equal to 0 at 0, 1, 2, and 3. But the thing is that at 0 and 3, we have endpoints. Now, that means there's no change in direction there, although the particle is stopped at that time, right? At time 0, 1, 2, 3, the particle is stopped. But again, like I said, because time equals 0 and time equals 3 are the endpoints of the interval, then that means that the particle can only change direction at t equals 1 and at t equals 2. So let's do a sign chart. Let's do 1 and 2. And let's plug in values for t that are between 0, because those are the endpoints, right? 0 and 3. So something between 0 and 1. If we do 1/2, and if we do sine of pi halves, remember that that is equal to 1. If we do 3/2, which is between 1 and 2, we're going to get that sine of 3/2 pi is going to equal -1. So notice that there is a change, definitely a change in direction. And how about after 2? Something between 2 and 3, 5/2. So notice that if we plug in 5/2, sine of 5/2 pi is 1. So that means that again, there is a change in the direction right here at t equals 2 and at t equals 1. So let's focus now on part B. So B says find the particle's displacement for the time interval between 0 and 3. So let's remember that finding the displacement is simply integrating the velocity function in the time interval. So we simply have to go integrate from 0 to 3 sine of pi t dt. And then if you do the math, remember that we're going to get minus 1 over pi times cosine of pi times t, and the interval is from 0 to 3. So this is going to give us negative 1 over pi times cosine of 3 pi plus minus minus, so we get plus 1 over pi times cosine of 0. And this is exactly 2 over pi, which is approximately 0.637. It's given in meters per second, so that means that this is going to be meters. Finally, for part C, they want us to find the particle's total distance traveled for the time interval between 0 and 3. Now remember that for distance traveled, we have to take into account at which time was the motion changed or stopped, right? So we know that at 0, at 1, at 2, and at 3, there was changes, well, not in the extremes, but we know there was changes in direction at t equals 1 and t equals 2. So that means that we have to integrate separately. So we would integrate from 0 to 1 the absolute value of sine of pi times t dt. That would be the first one. Then we would have to add this to integrating from 1 to 2. Again, this is a 2. Let me do that again. So absolute value of sine of pi t dt in this interval, and then the last interval from 2 to 3, absolute value of sine of pi t dt. And then if we do the math here, this is going to give us absolute value of 2 over pi for the first interval, plus absolute value of negative 2 over pi for the second interval, and then we get again 2 over pi, absolute value of 2 over pi for the third interval. And this is easy to add. It's just going to be 6 over pi exactly, which is approximately 1.91 meters. So in the next slide, we're going to talk about position and velocity from acceleration. Now, of course, if we integrate the acceleration, if we do the integration of the acceleration, this is going to give us velocity, right? And then obviously, if we integrate velocity, we're going to get the position function. So example 14.39 says, the motion of a falling parachutist is modeled as a linear motion by considering that the parachutist is a particle moving along a line whose positive direction is vertically downwards. The parachute is opened at t equals 0, at which time the parachutist's position is s equals 0. According to the model, the acceleration function for the parachutist's motion for t greater than 0 is given by acceleration in terms of time is equal to minus 54 times e to the power of minus 1.5 times time. So letter A, at the time or at the moment the parachute opens, the parachutist has a velocity of 42 meters per second. Find the velocity function of the parachutist for t greater than 0. And then what does the model say about the parachutist's velocity at t tending to infinity. So they want us to test the limit to infinity once we have the function. Okay, so to find the velocity, again, we need to integrate the acceleration. So we have to integrate minus 54 e to the power of negative 1.5 t. And this is a pretty straightforward integration. We know that this is going to be negative 54 times, because we need the derivative as well to do the u substitution. So that means that we also need to include 1 over minus 1.5. And this times Euler's number to the power of minus 1.5t plus c. And then from here, we are going to get 36 times e to the power of minus 1.5t plus c. But we know that at time equals 0, the velocity is 42, because they tell us that here, right? That means that c has to be found using this information. And we're going to get 42 minus 36. That's going to be 6. So c equals 6. So we might as well put that here. And there we go. So this would be the velocity function using the acceleration and integrating the acceleration, right? Okay, but there was another part of this question. It says, what does the model say about the parachutist's velocity as t tends to infinity? So what's the limit? What is the limit as t tends to infinity of 36, and I'm going to rewrite this as 36 over e to the 1.5 t plus 6. So what happens as this value increases, right? As this t increases, this e to the power of infinity is just a very large number. So that means that this tends to 0. If this tends to 0, we're only left with 6. So what that says is that the velocity is going to tend to stay at 6 meters per second. So for part B, they want us to find the position function of the parachutist for t greater than 0. Now remember that to find the position function, we simply have to integrate the velocity function. In other words, we have to integrate the function that we found before, which is 36 e to the minus 1.5 t plus 6 dt. So if we integrate this, we're going to get that this is equal to negative 24 e to the minus 1.5 t plus 6t plus c. But they told us before that at time equals 0, the position is considered to be 0. So if we plug in 0 here, say this equals 0, and substitute t for 0, we are going to get that c is equal to 24. Therefore, we have found the position function. This would definitely be 24 here. Then this will be the position function that models the position of the parachutist after the parachute opens for t greater than 0. So in the next slide, we're going to talk about uniformly accelerated motion. Motion under the effect of gravity in the vicinity of Earth or another planet is an important case of rectilinear motion. This case is called uniformly accelerated motion. So if a particle moves with constant acceleration along the s-axis, and we know the initial speed and position of the particle, then it is possible to have specific formulas for the position and speed at any time t. So basically here they're showing us how we can derive formulas for velocity and position based on the fact that you have uniformly accelerated motion. So what does that mean? Well, if the acceleration is constant, then we can say that a of t is equal to a, that the velocity at time 0 is v sub 0, or initial velocity, and that the position at time equals 0 is s sub 0. So notice that if we want to get the velocity, we integrate the acceleration. So if you integrate for a, you're going to get a times t plus a constant. But since we know that at 0, velocity is just v sub 0, so then we just plug that into the formula, and we end up with this here, which is the classical physics formula for velocity when you have uniformly accelerated motion. Then we can do the same thing for position, because then we would have to just integrate the velocity function, right, that we just found. So notice that if we integrate this here, which is this velocity function that we just found, we're going to get 1/2 at squared plus initial velocity times time plus c. But then again, because we know that the initial position is s sub 0, this is going to be the derived formula for position in classically uniformly accelerated motion. Then there's the case when this is applied to free fall, where we know that the acceleration is the force of gravity, which is 9.8 meters per second squared. And we can see that it's a simple substitution for a, substituting it for g, which again is the acceleration due to the effect of Earth's gravity. Okay, so here we are in example 14.40, which will be the last one on this video. And it says, a ball is hit directly upwards from a point 2 meters above the ground with initial velocity of 45 meters per second. How high will the ball travel? So the ball, there's already a height of 2 meters when the ball is hit, and they're asking how high will it travel? So we know that velocity in this case is going to be minus 9.8 meters per second, right, squared, which is the deceleration due to gravity. So this times time plus 45, which is the initial velocity, right? Remember that the formula says that velocity in terms of time is equal to acceleration times time plus initial velocity, right? That's one of the formulas that was derived in the previous slide. So that's where this comes from. Also, we know that position, we found that position is equal to 1/2 acceleration times time squared plus initial velocity times time plus initial position, right? So here, in this case, our position function, using the information from the problem, would be negative 1/2 times 9.8 times t squared, right? Plus 45t, because 45 is the initial velocity that we have here, plus 45t. And the initial position is 2 meters, so this plus 2. Okay, but we still need the time in order to see how high the ball will travel. But notice that velocity is going to equal 0 when the ball reaches the highest point, right? If you throw a ball straight up into the air, it's going to go up, up, and up until it stops. And that is due to the action of gravity, of course. So we have to solve for velocity equaling 0. So 0 equal to minus 9.8t plus 45. And then if we solve for t here, we're going to get that the time is approximately 4.6 seconds. So after 4.6 seconds, the ball is going to stop. So that means that we can now plug the 4.6 seconds into this function and actually find how high the ball will travel. Now, if we do that, that means that s of 4.6 is going to equal negative 4.9 times 4.6 squared plus 45 times 4.6 plus 2. And then from here, we're going to get approximately 105.32 meters.